What if I already had two sorted sublists and I wanted to combine them into a single sorted list? I could do this fairly simply by traversing each of the sublists from left to right and doing what's called a merge. So I have a reference to the beginning of the first list and a reference to the beginning of the second list. And I'm going to put these into a new list. And what I'll do at each step is compare these elements and take whichever one is smaller. So here, I'll put the 0 here. And since I grabbed a 0 from here, I'll advance this little index 1 forward. Now I compare the 1 and the 2. 1 comes next. This advances. Compare the 2 and the 3. 2 comes next. This advances. Compare the 3 and the 5. So the 3 comes next. This advances. 5 and 8, we get the 5. 8 and 6, we get the 6. And now this is out of bounds. So we know that the rest will come from here. We get the 8 and then the 9. So the specific operation we've just performed is a merge. And merging is one of the key operations of merge sort. Now, this merge operation in isolation runs in O of n time. And what we're going to do with merge sort is start with an unsorted array. We're going to keep breaking it down in half over and over again recursively. And then as those recursive calls return, we will merge the components in this manner. And so the overall cost of merge sort is going to be O of n log n. And I'll give a sort of informal argument for why that is later. But let's look at an example of the entire merge sort process. Here is an unsorted list or array. And for merge sort, we will first break it in half. So right here. In general, we break it roughly in half. This happens to be an array of even length, but if it's not even, then one side gets one more element than the other. It's no problem. And we do recursive calls on each of the halves. So there's a recursive call there, and eventually there'll be a recursive call here, but we'll save that for later. Because the way that the recursive call is actually executed is that we're going to sort the first half first, and then later we'll come back and sort that half. So we've broken it in half. We've done a recursive call on the first half. We repeat that process. Break this in half. Do a recursive call here. Break this in half. Do a recursive call here. And now we're at a point where we have a list or array of size 1. And if all we have is one element, then it's guaranteed to be sorted. So we're done. So what happens now? Well, back up at this level, we broke it in half, did a recursive call in the first half. Now we do a recursive call in the second half. So now we have 4 and 1. Now the merge has to happen. So the merges are going to happen as these recursive calls return. So as they return, we're going to put the elements into their correct spots with respect to each other. So we're going to notice that the 1 comes before the 4, and we're going to put the 1 here and the 4 there. And that basically means that these sort of recursive calls are done now. So we've returned back up to this level, and this subarray is sorted, but now we have to sort the left subarray. So we do a recursive call on 3, 6. Now you may have noticed this is already sorted, but that's not necessarily obvious to the code. So we're still going to break it in half and do a recursive call on the left. That's a sorted subarray. Recursive call on the right, it's a sorted subarray. And then we merge them, except it's already sorted, so the merge process is really just passing through and confirming that it's sorted. But that finishes, and we're left with that sorted subarray. Now, back up one level, time to merge these two. So I'll show this in more detail since there's more going on. As before, we start at the left end of both of these. We pick whichever one is smaller. So 1 comes first, then 3, and then 4, and then 6. And since these are merged, these recursive calls are done. But now we have to do the whole process on the right side. So first, recursive call with the elements on the right. Break that in half. Do the left side. Break that in half. Do the left side. We have 9. The right side of this is 2. When we merge these, they will change order and end up as 2, 9. Those calls return now. Now we do a recursive call on the right side. And then the left side of that subarray and the right side of that one. Now we merge those results, which means we get 0 here and 7 there. And then these recursive calls go away. And now it is time to merge these two subarrays into here. So we merge them. So starting with the 0 from there, then the 2, then the 7, then the 9. Then these recursive calls go away. And then finally, it's time to merge the whole thing back into its final form. So we'll get rid of all of this so I can demonstrate the process. So 0 comes before 1. 1 comes before 2. 2 before 3. 3 before 7. 4 before 7. 6 before 7. And then, since this array is done, we just plug in 7 and 9 to wrap it up. This goes away, and we are left with a sorted array. That's how merge sort works. In order to understand the big O time complexity of merge sort, let's solve this problem again, but show our work in a different way. So before, I was writing and erasing things, showing how the dynamic execution of the algorithm would look like. But now we're just going to leave it all out on the whiteboard here. So we do recursive calls. We split this in half. So we basically split it into a half here and a half here. And then on this side, we split that into halves again. And then this is split into halves here. So in terms of the actual values we're working with, nothing has been modified yet. But now we're looking at the 4 and the 1. When we merge those, we have to loop through these subarrays of size 1, and we actually modify the contents. So we have a 1 here and a 4 there. Now, back on this side, this gets split up in 2. And although we don't rearrange anything, we still have to sort of process these values into a merged subarray of size 2. Then we can merge these two subarrays. So we'll have 1, 3, 4, 6. But we can't merge this with this until we've recursively sorted this half of the array. So this half is split in 2, and then that left half is split in 2. Then we merge those two subarrays. So we have 2 and 9. And then we go to this side, split that in 2, merge the 0 and the 7, 0, 7. Now we merge that half with this half, end up with 0, 2, 7, 9. And now we can merge that with that, and we'll get a complete result. So we have 0, 1, 2, 3, 4, 6, 7, 9. So this time I have not erased anything. And what I said was that this would help us understand the big O time complexity of merge sort. So why is that? Well, every time that we merge subarrays, we're processing them from left to right. Now, I said earlier that merging is a big O of n operation. So merge is O of n. And of course, we're merging subarrays of different sizes. So when I am merging this array with this array, I'm essentially, doing roughly around 4 comparisons, give or take a little bit. But when I'm merging, this one with this one, it's closer to 8. So the size of the arrays is changing. However, notice that for any given level of this merging process, the overall number of elements that have to be merged in some way is n. Because here I'm adding up 2 plus 2 plus 2 plus 2, whereas down here it's 4 plus 4, but I still get 8 either way. There's 8 elements in this example array. So I'm going to do O of n operations some number of times. Now, in this example, I'm doing it 3 times, or roughly around 3 times. It could be slightly varied depending on if the array is perfectly divisible by 2 at every single level, which is a nice case we have here, but it isn't always so elegant. But why do we have 3 levels? Well, when you repeatedly split something in 2 over and over again, you're going to be able to do that roughly log 2 of n times. So why do we have 3 layers here? Because log 2 of 8 equals 3. And this O of n here is n. So overall, our O for merge sort is n log n. It's basically the area of this rectangle of numbers that I drew while solving this problem. So that's how merge sort works. We'll see next time how it's implemented.